All right. Good afternoon, everybody. Thanks for sticking around. So today I want to give the 0% robotics talk. I come, let's say, from the pedestrian dynamics community and specifically from the part of physics that deals with pedestrian dynamics. So my talk is going to be about understanding pedestrian dynamics. Now, I am a physicist. What does mean understanding? Especially for something that is about a crowd of pedestrians, right? So about particles that probably, they can have a thinking and so on and so forth. So as you will see, pedestrian understanding for us is about collecting really large-scale data. We speak about 50, 100 million trajectories about crowds, and then try to formulate statistical models about it. So, what you will see is a little bit the work that we've been doing in the group in the last 10 plus years. And let's say, okay, we started for two reasons, real quick, right? Understanding pedestrian dynamics means better construction of public infrastructure, but also at the same time, pedestrian dynamics is a very complex system, so it has deep connection with a lot of system of active particles from animals to, let's say, all sort of complex flowing matter. So as, let's say, physicists, we started with the challenge, okay, can we actually formulate an understanding of, how crowd moves? So it's a very, let's say, non-typical physical system because we deal with particles that have extremely high variability and then extreme, let's say, stochastic dynamics. Very hard to predict what one person will do. So what does it even mean to get to quantitative model of such a system? And so for us, real quick, the challenge became about characterizing probability distributions of trajectories of people or joint probability distribution of ensembles of people. So the business became characterizing or measuring such probability distribution and then modeling this joint probability distribution or some marginals thereof. So let's say to give the very brief overview about the very, let's say, diverse community that work in pedestrian dynamics, when it comes to characterize this probability distribution in path space, let's say, there is a very large cut of groups that really work in laboratory conditions. And so they, create, let's say, some sort of in vitro conditions, and then they track people, extract trajectory, and try to extract an understanding from it. We are on the complete, let's say, opposite side of the spectrum because, people live in some sort of real environment. So what we do to understand crowds is measuring really in real environment. And this is something that gives us the edge of measuring, let's say, for very, very long time on large scales. And this means, contrary to laboratory condition, being able to acquire, for instance, millions or tens of millions of trajectories, something that would be impossible in laboratory conditions. So the talk of today is going to be about, let's say, data acquisition and in real life condition. I will mention, a little bit what's happening. It's going to be about data set that range anywhere from thousands to tens of millions trajectories. And then, first of all, I will use the typical point of view of physicist, and then I'm going to try to explain some statistical behavior using simple models. Because we like to try to explain things simple, but then since we have such large data set, naturally we started to move in the direction of generative AI. And actually, we use the generative model to try to extract physics from the data set that we have. So first things first, I'm going to talk about really short about what we do with data. So let's say we really put sorry. Well, let me go one back. Yes, in previous year, we really put a lot of effort to acquire as much data as possible. So let's say most of our data acquisition techniques rely on arrays of overhead depth cameras. This is something that we have been deploying anywhere from things like train stations, festivals, let's say museums, and so on and so forth. Again, we would like of this system to acquire as much tracking data as possible, but we also did normal, vision type of endeavors, but also we tracked, we have data set about tracking people inside museum, for instance, tracking Bluetooth beacons or Wi-Fi like signals and so on and so forth. But definitely I would say most of our effort went into this compartment, so maybe some here knows what I'm talking about. Yeah, we discussed LIDAR in the morning. So We like to acquire data deploying arrays of 3D depth sensors, LiDAR or stereoscopic sensors. So we acquire, let's say, point clouds over relatively large area. As of now, we have entire train platforms that we have been tracking for like 4 years at 10 hertz non-stop, which means 100 million trajectory scale off. Here we have a case in which we track people over let's say a star case, but let's say these are all examples of data set that we acquire. Let's say we like a lot 3D depth because since it's not in the visible spectrum, it's not privacy infringing, and so it's easier for us to acquire data set in public spaces. So let's say over the last years, we really acquired in data in different conditions, even as I said, festivals and so on and so forth. So my let's say working condition typically is in some sort of infinite data limit. So imagine that you have been tracking crowds at, I don't know, traffic light for 3 years, automatically you are in the millions. So let's say data is infinite. This is a different limit than the infinite information limit, by the way. So we have measurements, but this doesn't mean having infinite information. But definitely, if one of my working condition was the ability to measure this probability of trajectory, this is what puts me in the condition of having an empirical sampling of this trajectory probability. And now I would like to do some modeling of it. So, well, there was a point in the morning that is, let's say, how Gaussian is what we see. Well, I would say in the limit of very many trajectory, nothing is Gaussian anymore. So I would like to start with something really, really simple. Let's say, imagine, tracking a single person walking, in the perspective of seeing this experiment of a single person walking straight, and you repeat this experiment 250 times, well, imagine that you plot the probability distribution of velocity. So the red is the longitudinal velocity in this direction, and the blue is the transversal velocity. This is a logarithmic plot, right? This means that Gaussian become parabolas. Now you see that at the scale of 250 trajectories, you have like a Gaussian fluctuation around 1 meter per second, let's say in longitudinal direction, and 0 meter per second around the transversal direction. But as soon as instead you look at 250,000 trajectories, yeah, okay, now you start having tails that deviate from the Gaussian behavior because you start having all sort of rear behavior, people stopping, people inverting their trajectory, there is a cut of population detrans, and so on and so forth. So the business is, first of all, understanding that the probability distributions that we deal with are non-trivial, and the second is modeling. So it's possible to do some sort of social force model, even of a single particle motion dynamics. It's about getting a correct noise structure. So for this, I will the first paper that was presented here is enough, but I would like to point your attention to a little bit more interesting case. That is what happens when you have two particles, interacting with one another and avoiding each other. This is also something very non-Gaussian that we have been looking at, a couple of million times. We tracked people in a train station and isolate all sort of avoidance behavior that you might have. And yes, yeah, it turns out that there is a very specific, also one can expect a very specific statistical footprint to what happens, and here I represented one marginal of it in the following way. So imagine that I put here on the x-axis the distance that these two particles had the first time they saw each other, so at the beginning of the process. Then the particle will walk in opposite direction and avoid each other, and the distance that they have when they avoid each other is on this axis. Now, the black line is the average of all the events sampled, and now of course what you see is that should you have head-on collision, then of course the two particles avoid each other. They will have a distance of about 75 centimeters, and then this avoidance process asymptotically as the transversal distance grows, there is fewer and fewer interaction. And this, as physicists, we were really happy because this whole probabilistic structure, including a few more other probability distributions, for instance, how much particles slow down, how many collisions statistically one have, and so on and so forth, can be already reproduced with something that doesn't need much of machine learning. It can be a social force model that has a right interaction structure, and the right noise structure is enough to reproduce even the very complex probability distributions that one might encounter in this. Now, let's say, clearly, when you have two particles studying the force process is perhaps kind of natural, but when you go to n-body type of interactions, then force models that you can estimate by hand are out of reach. Let me mention perhaps the simple case of n-body type of interaction. This is something that you immediately encounter when you study routing problems. So imagine this is a part of a big festival we have in the city, 150,000 people that walk around. And now imagine you are part of this big crowd here, and you are faced with the decision of taking a short path and a long path. This is possibly the most basic routing problem. So when there is sufficiently dilute flow, everybody takes short paths, but then the short path saturates, and then people start taking the long paths as well. All right, pretty simple. The thing is that even a process as simple as this comes with non-trivial statistics. So let me, characterize the statistics of this problem in the simplest possible way. Imagine to take snapshots of the problem, you count the number of people involved, and then you count the number of people that take short and number of people that take long path. So number of people in total is here, and then number of people that take short path is in red, number of people that take long path is in blue. So what you see is that if we have sufficiently few people, then everybody takes a short path, and then as soon as the system is loaded enough, then there is a combination of the usage of the two paths. Simple enough. The problem is that this is only one small part of the entire picture. It turns out that the problem has a very complex probabilistic structure in which, on average, the system uses the two channels as soon as you reach capacity, but there are pretty many situations in which people keep on using only the short path, so you have some sort of herding. Everybody blindly does a stupid choice. This happens with some sort of probability, and even let's say even such a simple problem has a very non-trivial probabilistic structure. So problem is, we have a system that is complex, can be characterized only in terms of probability distribution, and especially if one wants to do long-term prediction, I think characterizing probabilities, they are unavoidable choice. Well, to be honest, a system like this, now I will not enter into detail, is something that we could model as a n-body cooperative game, in which these agents sampling, having some sort of stochastic sampling of the system, and on the capability of the other agents make a binary choice. And let's say even a basic cooperative game can explain some sort of stochastic feature of the problem. So I don't want to enter into the details of the model. You can find the data set and the details here. And let's say this first part of the talk, in this first part, I wanted to point your attention at how stochastic the system is, and the fact that to understand and to do predictions, I think dealing with probability is unavoidable. What I would like to finish the talk with is what I think is a very interesting application of generative AI when it comes to having data sets that are at the scale of millions of trajectories. So I said at the beginning that when you go into crowd dynamics, there are two different schools. So people that do experiments in laboratory, very controlled conditions here. You can set up your map. So let's say you can set up exactly how people would interact in which scenario and so on and so forth. So you have a lot of parametric control. Opposite condition is a real-life condition. What we do, you have infinite data, but essentially zero parametric control, right? So this is infinite parametric control, but very little data. This is infinite data, but zero parametric control. And now I want to say with the generative AI, we can have a nice use case to sit in the middle. So this is something that I think is very interesting. So let's say what this is going to be about at first, it's going to be a, let's say, evolution of the, well, this is a social force model type of equation. If someone knows, it's the way typically crowd is modeled. So it's about modeling the acceleration of a particle in terms of some source of force between each pedestrian and the others. But here we have a model that instead tries to learn the acceleration of each particle, sampling a conditional probability distribution related to the particle itself, its history, the neighbors, and the neighbors' history. Okay? So for working on with this model, we use the tracking data that we collect at the train station. It's the entire platform, something like, as you will see, about 80 meters times 10 meters. Everybody got tracked. Actually, this is a data set. We have data for about 4 years. So it's, many millions of trajectories. And I would claim this is a data set that is that contains a lot of information. So imagine you have 100K trajectories per day times 4 years. It's a lot of information in the sense that there are co-flows, counter-flows, people waiting, and so on and so forth. The problem is that information is very sparse in such a data set, right? So it's very hard to retrieve a relevant element to the specific problem you are considering. For instance, if you want to look at, unidirectional crowds, they happen, but happen only a few times per day. So you would need to find all the instances of a given experiment and so on and so forth. So information exists, but is extremely sparse. So let's say with what I'm going to present, I want to make a point that we can use generative AI as a sort of way of querying information that is inside the data set. Okay? So first of all, here we, let's say, worked out I would say a fairly standard structure, autoregressive generative model for the end-body interaction. So we had, let's say, maybe I can go to this. So a system or a model with the following structure. It's a model that tries to predict the probability of acceleration of each particle over here. It happens in an autoregressive way. So we try to predict the probability step after step after step. At each time step, we have a message passing algorithm, so pedestrians essentially talk to one another through a graph. There is a conditional VAE step, so let's say every particle samples from a Gaussian and then learns how to, let's say, remap this sampling into a latent signal that then is passed to all the other pedestrians, and this is effectively used to predict the acceleration in the next time step. Now, why is this interesting? Well, here there is a couple of movies. I can tell you that the dynamics is not distinguishable, but this is not very believable, right? So then to validate the model, we started really looking into fine detail probability distribution and the capability of the model of recovering the fine detail probability distribution that we have in the data. So we started for very simple things, velocity distribution in different directions, fundamental diagrams, so for instance, how velocity and density scale, but also what is the structure of the fluctuation of the scaling of velocity. See that here we have the generative model reproducing the probability distribution, for instance, in velocity, even in logarithmic scale, right? So this means nailing event that happens 1 in 1,000, 1 in 10,000, and so on and so forth. And let's say, in this paper, you can find all sorts of validation on, for instance, characteristic correlation function in time, so how the velocity or position signal decorrelate in time, a typical occupancy in space, and so on and so forth. So, long story short, we were very happy to have a model that could reproduce statistics in a large data set. But then the question is, okay, so what? Having a model is interesting, can we do something interesting with it? As I said, I believe in this large data set information exists, but is very sparse. So, can we use this generative model to understand something about the problem? So actually, we started using the model to replay experiments whose results are known in the literature, but they have not been part of the training set of the model. So let me reconnect to something that I showed a few slides ago. So let's say we studied, for instance, very extensively the problem of, do I get to see the movie? We studied very extensively the problem of pedestrians avoiding each other. So we said, okay, I have a model, has been trained with infinite data. Can I get my model to predict realistically what is the avoidance dynamics of two pedestrians? So we initialized the models with pedestrians in an head-on configuration, and we asked to which extent is my model repredicting the results that I had information from past experiments. And we were very happy to see that, let's say, for instance, this avoidance curve was pretty decently reproduced without any of the specific avoidance scenario being in the data. And to be honest, the model learned by itself a force expression very similar to what we had inferred manually. We, let's say, in our previous paper said, okay, we have an interaction cone that is about 20 degrees. The model learned by itself that we interact with a vision cone that is about 26.6 degrees. So this was pretty good news because, let's say, again, the model was not trained anywhere explicitly about this stuff. So to conclude, we said, okay, then let's do something interesting. Let's try to probe configuration that nobody knows about. For instance, how does one particle interacts with n other particles, okay? So is the interaction additive, is interaction topological? So do you interact with the sum? Let's say, do you interact in an additive way? So you sum individual interaction, you interact only with the closest one, and so on and so forth. So in physics, this is a pretty important question. And let's say, luckily, what happens is that scenarios like this in our dataset are sparse, but they are still relatively frequent. So we have something like 10 to the power 5 cases similar to this. They're just very hard to find. They are anywhere in the station happening. And so, well, turns out that we could show that essentially the model like the one that we trained behave as a social force-like model, but with a topological interaction. This means that essentially it would select, it would decide the next step based on a sort of top K social force-like interaction. So essentially, we have an additive structure. We interact with, top K people around us with K around 10. So let's say the model learned to check interaction with the 10 closest neighbors. And we were pretty happy about this. Let's say in the physics literature, topological interaction have been proved, for instance, for birds. Like birds interact only with the 5 closest birds and not with the others. But it was still impossible to check this for people. So I'm at the end of my time and the end of my talk. So let's say the take-home message, I would say, is the following. As physicists, we are interested in crowds, and the game becomes interesting for us only when big data is present, because what we want to do is being able to explain the statistics pattern that we find in the data. So here I wanted to give the gist of the fact that in many conditions, simple models are possible. Actually, we have many papers in which we estimate the noise structure for social force models, noise structure for games, and so on and so forth. But yeah, here I didn't focus on this, but please, check, for instance, on my website if you're interested. We have a few tens of works about this. But then the latest stuff is about using generative AI as a tool to explore this very large data set. So again, we have infinite data, but knowledge is very sparse. And I think your generative AI model actually gave us a possibility to explore data set in a way that we couldn't do before. And with this, I thank you for your attention. Yeah, thanks.
Thank you so much for this interesting talk. Are there any questions in the room? Please.
Oh, thank you for your presentation. So here that may I know the application of these models? And so this is the first short question. And second, have you considered if we involve robotics, mobile robot in the environment, and how can you predict the behavior of pedestrians? Thanks.
So thanks for both questions. So let's say typical application are for this class of model are much more present than you might think. Like big airports now are designed using a crowd simulation software to make sure that the crowd can evacuate the airport in case of problem. The big deal is that the vast majority of these models didn't receive any level of quantitative validation, but we are happy now to have the data to start actually validating this class of models. And about robots, I think this is a very interesting direction. I think there are a lot of possibilities that are opened when you put robots inside a crowd. I wish to move in that direction, to be honest. I'm not there yet. So if anyone has a willingness to collaborate, we have a lot of crowd expertise, access to experiments and big festivals. We don't have the robots expertise. So let's say I would be happy to talk further about this.
Thank you.
I'm pretty sure after this talk you will receive at least 10 emails. Which
Let's see.
So thank you very much. Amazing talk. I just wanted to, because the statistics that you presented at the beginning, when you said it's essentially not Gaussian, especially when you go to the limit, I was wondering, you basically use all the data that you have and throw all of them into one bucket. Whether you could, for example, get quite far already by having something like a norm behavior and then plus anomalies. Whether this could lead to let's say improved capabilities to use these models, or whether you could say I have I cluster the conditions and I know that under certain conditions the people behave, for example, when they're drunk they behave completely differently. So I was wondering about these directions.
So okay, fantastic question. So two answers. Answer number one. Here, okay. Answer number two first. So the big challenge, as I said, we are in the infinite data limit, but not infinite information limit. And the difference is that, let's say, we have trajectories, but identifying different scenarios at these scales and in a scalable and fast way is non-trivial, right? So imagine that you have this gigantic collection of trajectories, and now you need to tell this is similar to that, which is similar to that, which is similar to that. So we have papers in which we have a graph-based approach in which we try to, let's say, attach a meaning to the scene that we observed in order to cluster as quickly as possible. But at least for us, this is a problem that is very far from solution. So maybe in this community here, you have...
Let's talk
about it.
Yeah.
This is, let's say, doing automatic classification at scale is something I'm interested into. You also need to consider the fact that when the map is so large, you have different instances of different type of scenarios happening at once in different places, right? So this is very non-trivial, I would say, because at the scale you have a map of 1,000 square meter, and here something happens, there something happens. So doing it at scale is non-trivial. Having said that, let's say, of course, the more you put conditions on the data, the more the statistics changes and becomes easier or harder to model. In what I showed at the beginning, there was a very first level of conditioning on the data, and then the key modeling was all the rest of the variability is something that I'm going to explain with noise. Let's say there is a base model plus additive noise. The problem then becomes what is the best additive noise. Of course, the more conditions you put, maybe the easier the job becomes, but also putting more condition is intrinsically non-trivial. If you have good recipes on putting good condition, I'm all ears. So it's just that my plan is pretty soon, so let's make it quick. And
I don't have them, right? But let's talk
Yes.
before you leave. Yeah.
Yes.